high discrepancy from the observational data in certain situations. But as the practice show, as the observation show, this law works very well in solar system. As far as the planets are concerned, the motion of planets and asteroids and comets and the motion of artificial satellites orbiting the Earth, this law works perfectly. However, we are practically sure that this law is not an ultimate law, because it was derived from experimental data, which are always observational data, which are always approximate. So there is a question: can this law be somehow obtained theoretically? Can it be derived from some fundamental principles of physics rather than from experimental observations? The answer is yes. This law can be derived, and it was derived from within the Einstein's theory of general relativity. The general relativity can produce this law. The general relativity is the theory about gravitational interaction, which takes into account relativistic effects. And Newton's law of universal gravitation can be obtained within the frames of more general theory, general relativity. But when we derive this law, we have to assume that the gravitational fields are weak and that the velocities of these objects are small compared to the velocity of light. And within this approximation, we can obtain the Newton's law. If the velocities are high or comparable to the velocity of light, or the gravitational field is strong, then this law will be incorrect. And more general formula will be needed to analyze the observational phenomena. And more general approach is provided by the general relativity theory. So this law is derived theoretically under the assumption that the velocities are small compared to the velocity of light, the velocity of motion of these two bodies are small, and the gravitational field is weak. What is weak and what is strong, that's another question. But within the solar system, we have weak gravitational fields. The strong gravitational fields emerge near the black holes. We have no black holes here in the vicinity of our star. So we have weak gravitational fields in the solar system, and this law therefore works perfectly. But anyway, some discrepancies were found between the predictions of this law and the real motion of planets. The real motion of planets is somewhat more complicated than the Newton's law predicts. If this is the Sun and this is the planet, the trajectory of planet's motion is very close to a circle, but actually it's not exactly a circle, it's an elliptical trajectory. I will draw this trajectory in an exaggerated way, showing you that the ellipse is very well distinguished from the circle. But anyway, this ellipse is very close to a circle. I'm just drawing it in this way so that everything will be clear to you. So when a planet is moving along this trajectory, it makes hundreds and hundreds of revolutions, hundreds of years for this planet. And gradually, this main axis of the ellipse is actually rotating, so that in 100 years, the ellipse will be, this axis will be something like this, and the ellipse will be something like this. So the ellipse is slowly rotating around the sun, around one of its, around the focus. And this slow rotation of the main axis cannot be predicted using the Newton's gravitation law. This is something which can be described, this slow motion of the main axis of the ellipse. It can be described within the general relativity theory. But this motion is very slow, and in the first approximation it can be neglected. But anyway, it's observed. This is an observable effect. So the general relativity has its influence even in weak gravitation fields like in our solar system around the sun. And there are many effects of general relativity that should be taken into account if we want to make correct predictions. So the Newton's law of gravitation is very good, but it's anyway approximate. Approximation is very good. The discrepancy with the observational data is very small, but anyway it's observable, it's there, it's present there. And the general relativity effects are very important even in our everyday life. Nobody knows, few people guess that when you have a navigator in your smartphone, the navigator works taking into account the effects of general relativity. If you don't take into account, at first when the engineers created the navigation system, the GPR system, Global Positioning System, when the GPS was first created, the engineers did not take into account the effects of general relativity. And what happened? They discovered that any coordinate on the surface of the planet Earth is well defined by the GPS system, but next day this coordinate moves a little bit, a few meters away, and then it moves again a few meters away. So every day the coordinate is determined with some mistake, with some error, and this error grows in time. It increases every day and becomes larger and larger. And from dozens of meters, it becomes hundreds of meters, and then it will become kilometers. So is it acceptable to determine the coordinates with the precision of a few kilometers, with a mistake of a few kilometers? No, it's absolutely unacceptable. People want to determine the coordinates exactly, well, like a few meters, plus minus a few meters, but not a few kilometers. What was the reason behind this constant shift of coordinates determined with the help of GPS system? The reason behind it was that there are some effects of general relativity which were not taken into account originally. And then when the engineers referred to scientists and discussed this problem, and the reason behind this discrepancy was found, and the effects of general relativity were taken into account in the software of, in the mathematics of GPS system, then the coordinates were determined with much more accuracy, with much better accuracy. So the effects of general relativity are observable both in the solar system when the planet's trajectories are somehow distorted, and also in our everyday life here on the surface of our planet. These effects of general relativity are well observed, and if they were not taken into account, we would have no precise GPS system. It would not work. Okay. After this small introduction, let me solve some problems with you, some physical problems. And the first problem I would like to consider is orbital velocity. Orbital velocity. So when a satellite moves around the Earth along the circular orbit, the satellite has some velocity. And its orbit has some radius, that is the distance from the center of our planet. And the velocity and the orbits that we will consider are very close actually to the surface of our planet, so that this distance, delta h, is small compared to radius. So delta h, the height of the orbit is much smaller than the radius of our planet. The radius of our planet is about 6,400 kilometers. So we will consider such orbital motion that the height of the orbit above the surface of the Earth is much less than 6,000 kilometers. What does it mean? Well, it must be less than 500 kilometers, less than 1,000 kilometers. That's enough. Less than 1,000 kilometers. That's already much less than 6,000. If this delta h is small, then the moving satellite will have acceleration, centripetal acceleration, directed to the center of our planet, and that will be almost equal to the acceleration of free fall on the surface of our planet. Almost the same. So we can assume that the acceleration of free fall is the centripetal, equals the centripetal acceleration of the satellite that moves along the circular orbit. And the centripetal acceleration is well known. It's velocity squared over the radius of the circular orbit, over the radius of this circle. From here, we immediately obtain the velocity that must be equal to acceleration of free fall times the Earth's radius. If we substitute for these physical quantities their values, 9.8 meters per second squared for the acceleration of free fall and about 6,400 kilometers for the radius of our planet, then we can approximately calculate the velocity of a satellite which orbits the Earth. And this velocity will be something like 7.9 kilometers per second. That velocity is called orbital velocity. You can carry out these calculations yourself. It's not a complicated problem. So any satellite that orbits the Earth occupying a low altitude orbit, low altitude, it means less, the height of the altitude above the Earth's surface must be less than the Earth radius, much, much less. Any such satellite must have velocity something about 8 kilometers per second. About 8 kilometers per second. That's the velocity that the rocket booster must give the satellite. What happens if the velocity is smaller? Then we will have a planet, and if the velocity, well, imagine a high mountain. There is a high mountain, and we throw objects from the top of this mountain. And we throw objects horizontally. If the velocity is small, then the object will fly along the parabolic trajectory. That will be close to parabola on a small scale. Actually, it will be a part of elliptical motion, but on a small scale it looks like parabola. If the velocity is higher, then the object will fly to a longer distance. But if we increase the velocity, the object will fly even longer and longer for a longer distance. It will go farther and farther from the point of launching. But if we manage somehow to provide the velocity of about 8 kilometers per second, then with such a velocity the body will go around the Earth and will be found on a circular orbit. And this velocity is an orbital velocity. Let's give it the subscript O. So this is the orbital velocity, almost 8 kilometers per second. And in such circular motion, any object will have a centripetal acceleration, which is practically equal to free fall acceleration. That is why people say that every object in the satellite, inside the satellite, is falling down on the surface or on the planet with the free fall acceleration, and the satellite itself falls down with free fall acceleration, and all the objects inside it. And therefore we have weightlessness, the state of weightlessness, because both the spaceship itself and everything inside it fall down with the same acceleration, with the acceleration of free fall. And therefore the object inside fall down as the satellite moves along the circular object. Everything falls down, everything has the centripetal acceleration, the same centripetal acceleration, all the objects inside the spaceship. And therefore these objects don't move and don't accelerate with respect to the spaceship. With respect to the spaceship, everything inside flies freely without any acceleration, and that's such a state is called weightlessness. It means that nothing has weight inside this. What is weight? What is the weight of a body? The weight is a force with which a body of mass m acts on a balance. So this is a balance, and the balance is used to weigh the objects, and the force with which, and the force is sure to be the force with which the object acts on the balance is mg, and this is the weight of the body, the weight of the body. So if you try to weigh a body, an object on the balances inside the spaceship, then both the balances and the object and the spaceship itself will move with the same acceleration to the center of the planet. So there will be no force acting from the object on the balance surface. So you cannot weigh it. Any attempt to weigh the object will give you zero weight. No weight at all. No force of interaction. That is the weightlessness, the state of weightlessness. So if you impart a large velocity to a body, then it will go at some elliptical trajectory in this way. That will be the trajectory of motion if the velocity is larger than the orbital velocity. If you give the velocity larger than 8 kilometers per second. And if the velocity is even more larger, then the trajectory will go farther from the planet. And if the velocity is high enough, then the body will go to the infinity and will never return back to the planet. And now we will have to calculate this velocity, which is called the escape velocity. The escape velocity, which is associated with such a motion which does not coincide with any elliptical orbit, but which goes to infinity. And the body having such an escape velocity will escape the gravitational field of our planet and will travel to interplanetary space. Okay, let's consider this situation. So first of all, let's consider some orbit of radius r, circular orbit, and assume that some object was lifted to a higher orbit which is by delta r, which has the radius by delta r larger than r. So the radius of this orbit will be r plus delta r. Any object here on this height, on this distance from the center, from the gravitational center, will experience a force of universal gravitation. And if we move the body upward a little bit, we will have to perform some work. And the work is F delta r. We assume that the delta r is so small that F does not practically change when you move the body upward. On this distance, the force F remains practically the same. So we can, it changes certainly, but the change is very small. We can neglect it at first approximation. So the work performed to move the body upward can be calculated by this formula, where F is the force of universal gravitation. So this force must be, this expression must be substituted for F here to calculate the work performed. If we move the body slowly, not changing its kinetic energy, then all this work will go to the change of potential energy. So that will be the change in potential energy. What is the change of potential energy of the body? This is the potential energy at the higher orbit minus potential energy at the lower orbit. And if we take into account what expression should be substituted for F, we obtain gamma small m capital M over r squared times delta r. Analyzing the units of measurement of this quantity, analyzing its dimension, we can easily observe that meter squared is in the denominator of this formula, while meters are in the numerator. So in this formula we will have meters in denominator, just meters, not meters squared. That is, if we analyze dimension. So we will have gamma small m capital M divided by some meters, no meter squared. And this dimension analysis indicates that the function of the potential energy as a function of r must be something like gamma m r. R to the first power, no square, because analysis of dimensions show that only meters can be in the denominator. So we can assume that the potential energy is expressed by this formula. And to prove this, it's very easy to prove this, is we take this formula and substitute it here to this expression. Then we obtain that potential energy at a higher orbit, r plus delta r, minus potential energy at a lower orbit, I will, because I know the correct answer, I will immediately put a sign minus here. You understand that any analysis based on dimensions can give you the formula correctly without an exact information about the numerical coefficient here. The numerical coefficient can never be determined from the analysis of dimensions. The dimensional analysis can only give you the approximate functional dependence on all the physical quantities here, but it cannot give you the numerical coefficient. And as I know the correct numerical coefficient, I will immediately take it into account to show that it works. So we substitute this expression here in this formula, and we obtain that minus gamma m capital M can be taken out of the round brackets, and what remains here is 1 over r plus delta r minus 1 over r. And if we calculate it, we obtain minus gamma m capital M. And here we will have r plus delta r times r. And here we will have r minus delta r. So r is cancelled. This minus and this minus gives you a plus. And what we have finally is gamma m over r plus delta r times r. But we know that delta r is very small. It's much smaller than the radius. So we can neglect it here. It's very small. And we obtain gamma m over r squared. And I have forgotten to take delta r in this formula, and so delta r is here. Delta r. Finally, we obtain the same formula from which we have started. This is the same. So we knew beforehand that the work performed equals this expression. We knew beforehand. And we assumed that the potential energy is expressed by this formula. And we know that the work performed equals the difference in potential energies in the higher orbit and in the lower orbit. And we used this assumption and substituted this formula into our expression and came to the same formula which we already know. We know that the final answer must be equal to this formula, and we obtained it. Therefore, our assumption about the potential energy formula is correct, and so we can finally write that in a gravitational field of mass m, any body of mass small m which is placed at distance r will have a potential energy equal to minus gamma small m capital M over r. This formula is correct. We have just proven it. This is the potential energy as a function of radius. It can easily be depicted on a graph. So if radius r goes to infinity, then the infinite number in denominator will cause all the expression to tend to 0. It's almost 0 at infinity. 0, but very small number, but negative. So very small negative number is here, but if radius r becomes smaller and smaller, the potential energy will become larger, but still negative. It will become larger negative number. So that's the potential function in gravitational field. The potential energy of a body of mass small m, lowercase m, of any mass in a gravitational field of another body has this potential energy. Now, if this is the radius of the planet, then outside the planet the potential energy is described by this function, But what happens inside the planet, we don't know. We will solve this problem separately. That will be a separate problem. Actually, I can tell you immediately that something different will happen here, and in the center of the planet the potential energy must be zero. Oh, no, not zero, but some other some different constant. So what happens inside the planet, we will consider this separately. But what happens outside the planet at the distances larger than the radius of the planet, we know very well. So if the object is on the surface of the planet and we want to send it far away from the planet to interplanetary space, then we must give this object a high kinetic energy in order to overcome this potential energy. We know that when the object moves, then its mechanical energy is conserved. And mechanical energy is kinetic energy plus potential energy, and it must be constant while the body moves. In gravitational field. So if we know the kinetic energy and we know the final energy, which is zero, then we know the kinetic energy. We can easily calculate it. And from this consideration, we use this equation for energy conservation. Kinetic energy is mv squared over 2, and potential energy is minus gamma small m capital M over r, and all this must be equal to constant. What constant? At very high distances from the Earth, we assume that the body goes far away from the planet, far away from the Earth. Its potential energy will be zero, and we assume that its kinetic energy also will be zero. So we calculate the minimum kinetic energy which is needed to go at infinite distance from the planet. The minimum kinetic energy means that at large distances the velocity of the body will be very small and the kinetic energy will be very small, like almost like zero. So all this is zero, and from here we obtain the velocity. The velocity squared will be gamma 2m over r, and so the velocity will be square root of gamma 2m over r. That's the escape velocity which is needed for an object to leave the planet, to go at infinite distance. And if you calculate it, you will obtain something like, if I'm not mistaken, 11.2 kilometers per second. If I have good memory, I don't remember the number. Something like 11 kilometers per second. So, if the velocity of the body is smaller than the orbital velocity, the body will fall on the surface of the planet. I will again show you this picture when we launch spaceships and space vehicles from a high mountain. If the velocity is smaller than the escape velocity, then the body will fall on the surface of the planet. That is, its initial velocity is smaller than the orbital velocity. If the initial velocity equals the orbital velocity, the body will move in its orbital trajectory. That is, the initial velocity equals the orbital velocity. If the velocity is higher than the orbital velocity but smaller than the escape velocity, then the trajectory will be elliptical. So this is the velocity of the body is higher than the orbital but smaller, is less than the escape velocity. So between something like between 8 and 11 kilometers per second. If the initial velocity is between 8 and 11 kilometers per second, then the trajectory will be elliptical. But if the velocity is larger than the escape velocity, then the body will go to infinity. If its initial velocity is larger or equal to escape velocity, then it will go to infinity. If the velocity equals the escape velocity, then the body at large distance from the Earth will move very slowly, and the larger the distance, the less the velocity of motion, and at infinite distances the velocity will be zero. But if the initial velocity is larger than the escape velocity, then the body will move at non-zero velocity forever, will move away and away from our planet. Such is the situation with orbital and escape velocities. So if you want to launch a satellite which will never fall on the planet and which will not leave the gravitational field and go to infinity, the velocity must be between the orbital velocity and the escape velocity. The velocity of any satellite must be between these two values. Actually, this is not quite correct, because I considered only the velocities of low orbital motion. If we take into account the possibility to launch the satellite to a high orbit, then we will discover that the velocity at this high orbit is less than the orbital velocity, less than the 7.9 kilometers per second. But this is a separate issue, and we will consider it if we have time. So we have found the potential energy of a body of mass m, which is in gravitational field of the planet, and the potential energy as a function of distance between the body and the center of the planet is given by this function. This is the formula for this function, and this is its graphical representation. What happens inside the planet? What will actually happen here inside the planet? If we dig a well, we have a planet of radius r, and we dig a well here and go closer to the center of the planet at a distance r, then what will be the potential energy here? Or we can put it in this way: what will be the force of attraction of this small body to the center of the planet if the planet has mass m? What will be the force of attraction? If the body is on the surface, we know, well, the force of attraction here will be given by the law of universal gravitation. This is when small radius equals the radius of the planet on the surface of the planet. But if the small radius is less than the radius of the planet and the body is somewhere here, what force will act on it? In order to answer this question, we have first to consider a much simpler problem. Consider a hollow sphere. All the mass of this sphere is concentrated on its surface. And inside it's hollow, it's empty. Inside the sphere is empty. And consider a small body M somewhere inside the sphere. And this is the center of the sphere. What forces will act on this small body inside such a sphere, which is empty inside, and all its mass is concentrated on the surface? And the mass is distributed evenly over the surface. It's a uniform distribution of mass, but inside it's empty. So, in order to find the force acting on this body, we choose any direction, arbitrary direction, and we choose a small solid angle alpha, which is alpha here and here. What is a solid angle? A solid angle cuts some area on the surface. It cuts some area on the surface. So it can be put like this. So this is a part of the surface of the sphere, and this is some area S, and the solid angle cuts this area, or indicates this area on the surface of the sphere. And then in this case, this angle by definition equals S divided by radius of the sphere squared. This is the radius of the sphere. So by definition, and this the units of measurement of such solid angle is st-radians. St-radian. If we measure a simple flat angle alpha is measured in radians. Radian by definition is the length of this arc delta L divided by the radius. Then we will have the angle, that is the flat angle on the surface, the angle on the surface. That is delta L, the length of this arc, divided by radius. And this angle is measured in radians. 1 radian is when the length of the arc equals the radius. This is about 56 degrees. That is 1 radian. The total angle, 360 degrees, is 2 pi radians. And here, when we have solid angles, we must use a different unit of measurement, which is called st-radian, and its by definition is the square of the area on the surface of the sphere divided by the radius of the sphere. So this is just a definition how to measure a solid angle or spatial angle. A simple example of spatial angle is the corner of the room. There you can see a spatial angle. A simple example. So here, if we consider this spatial or solid angle alpha, it will determine some area here, delta S1, and some area on the surface of the sphere, delta S2. the mass of this part of the surface of the sphere, m1, equals the density of the sphere, surface density, let it be sigma, times the area. And the mass of this part will be, again, the surface density of material times its area. By the way, this is the definition of surface density. The definition, what is the surface density? Is the mass in kilograms of a single 1 square meter of the surface square. 1 square meter of the surface area. So this is the definition of surface density, and we use this definition to find the mass of this part of the surface area and this part of the surface area. So this mass m will experience an attraction to this mass due to forces of universal gravitation, and that will be the distance r1 from between the chosen mass and the surface area here, and that will be the distance r2 between this mass and this surface area, and again another force F2 will be directed here, and force F1 will be directed here. The attraction to this surface area, delta S1, and the force of attraction to this surface area. There are forces of attraction due to the law of universal gravitation. And we can easily calculate the force F1, which must be gamma small m times the mass of this surface area, which is m1 over radius r1 squared. And that will be gamma m. What is m1, the mass of this surface area? Sigma delta S1. Sigma delta S1, the surface density over r1 squared. And delta S1, using the definition of a spatial angle, or in steradians, we can say that delta S1 must be equal to this angle alpha, which is a solid angle, times radius r1 squared. This is from definition of what is angle, what is a solid angle. So we use this expression to obtain gamma small m sigma, and for delta S1 we substitute alpha r1 squared and divided by r1 squared. So we obtain gamma m sigma alpha. That is the force F1 acting in this direction, upward. The force acting on this body from the small element of the surface of the sphere. Now we can calculate F2, and it's easy to understand that F2 will be the same, because radius r1 cancelled here, and so in the same way radius r2 will cancel from another formula which is absolutely similar. So that will be the expression for force F2. We have forces of gravitational attraction upward and downward along the arbitrary direction, and these forces turn out to be equal to each other. So in this direction, the net force is equal to 0 in this direction. If we choose any other direction, the same result. We obtain the same result. Again, all the forces in other directions will be 0. Therefore, the net force acting on this mass inside the hollow sphere is 0. If we take the hollow sphere, the empty inside, all the mass of this sphere is spread along the surface of the sphere, then any small mass inside it will experience no gravitational attraction to this sphere at whatever point inside the mass is located. The total gravitational force acting on this mass inside the sphere is 0. That's what we have proven by this simple geometrical consideration. choosing arbitrary direction and a small spatial angle, a solid angle, and just the definitions of what is solid angle. And using the law of universal gravitation, we prove that forces along this direction are equal. F1 is equal to F2. So the resulting force is 0. At whatever place, at whatever point inside the empty sphere, you try to measure the gravitational field, it's 0. Inside, there are no gravitational fields. All the gravitational field of the sphere is located outside the sphere, in the outside space. So, if we have no forces inside, then we can easily draw a graph showing the dependence of the force of universal gravitation acting on a body, located at distance r. I want to make a small remark concerning your studies. Whatever we discuss here during our lectures, you may find this material in the textbook. And in the textbook, you are given, everything is derived and explained in great detail. Everything is excellently explained. So if you don't understand anything during the lectures, if you miss any derivation, please check in the textbook and look into this paragraph and study the text, study all the arguments and reasoning, and you will understand it, because everything is explained perfectly in the textbooks I have given to you. Actually, any issue we discuss here is explained in the textbook, so you may read the textbook and the textbook in physics by academician Landsberg, and you will find an excellent explanation with all the details. So, if we have a planet of radius r, and we make a well, a deep well here, and put here a small body m, then what force will act on this body? We understand that if we imagine a sphere of radius small r, and this is capital R, if we imagine a sphere of radius small r, then this sphere will attract the body m. And the force of attraction will be given by the law of universal gravitation, where the mass here, the mass of the sphere inside radius r, here is the mass m inside of inner sphere by radius r squared. And all the material placed outside the small sphere will act on this body with zero force. We have just proven that if we take a thin sphere here with a thin walled sphere, then anything inside it will not be influenced gravitationally by any matter which is outside the sphere of radius r. The gravitational attraction to all this layer, spherical layer, will be equal to 0, because the mass is immersed into a deep well. Everything which is outside the small sphere will not actually act on this, or the action will cancel. The action of all these masses which are outside the small sphere will cancel each other. So we may not take into account the action of outside material. We have to take into account only the interaction with this small sphere of radius r small. And the only thing we have to find here is the mass of this inner sphere, of this small sphere. And the mass of this inner sphere is the density of material, which we consider to be constant. We believe that the matter is distributed evenly throughout the volume of the sphere. So the density, which is constant, times volume of the inner sphere r squared. And this gives you the density. What is volume? Is 4/3 pi r cube. And this is r squared. And it gives you, finally, gamma m density 4/3 pi, and all this divided by r. The first, all this divided by 3 cube and 3 and to the power of 3 r cube and r squared will give you r here. So some coefficient times radius, because here we have square and here we have r to the 3rd power. So we will have radius as a coefficient here. So the force acting on the body will be directly proportional to the distance to the inside, to the smaller sphere. So, and outside this body, outside this spherical mass, the force will be given by a usual formula where the r is the distance to the center. So if this is the capital R here on this graph, this is the surface of our sphere. Outside the sphere, the force is given by this formula. And inside the sphere, inside the Earth, for example, the force of interaction will be given by this formula, and it will be directly proportional to r. And when r equals 0, the force also equals 0. So if we go deeper and deeper inside the planet, the force of attraction to the center will become smaller and smaller. And in the center of the planet, the force will be 0, the force of attraction. Certainly, when the body is here, it's attracted to, it cannot be attracted to any direction, because all the directions are equivalent. So the force is directly proportional to the distance to the center here, and it's inversely proportional to the distance squared when you are outside the sphere, outside the planet. Well, that's the gravitational forces inside the planet, inside the solid sphere, filled uniformly with mass, with uniform distribution of mass, with constant density. And now we will be ready to solve the problem which was mentioned during the last lecture. After all these derivations and results obtained, it will be easy to solve the problem. Let's consider a solid sphere with the center in point C and radius r, and the mass uniformly distributed throughout the volume of this sphere, and its mass is m. And let's consider a spherical hollow place inside, a spherical cavity inside the sphere. Inside the main body, we consider the spherical body. And so that the mass contained in this small sphere, the mass contained here is m1, and the mass contained in all the remaining body, the mass contained here in the remaining volume will be, well, say m2. So that the total mass of the sphere, of the spherical body, if the cavity is filled with matter, just like anywhere else. If the cavity is filled with matter, the total mass will be m1 plus m2, if there is no cavity here. But we know that the cavity was created, somehow the matter was taken out of this volume, and so we have a hollow spherical space inside this sphere M. So the final mass, when this mass M1 was taken away, the final mass of the remaining body is M2. The final mass is M2 of this body. And there is any small point here, any small body with the mass mu, and we have to determine what force acts on this small body from the mass m2, from this, well, complicated form, a body of complicated form, spherical form with a hollow sphere inside, with a spherical vacancy, with a spherical cavity inside. Let this be a center of the small sphere, a center O. And let this be the distance r1 from the given point mu to the center of the small sphere. And let this vector be a distance r2 from this point mu to the center of the large sphere. First of all, we suppose that nothing was taken away from this region. This is not empty. We forget about that this is empty. We assume that this spherical region is filled with matter in the same way as all the other volume. So the mass m is here. We start from this simple case. The mass m is here. So in this situation, we will have a uniform sphere with mass m, and the matter is uniformly distributed along all the volume, and there is no such small sphere. We can just imagine that there is some volume, but it's filled with matter, and the mass m1 is here actually. What will be the interaction of mass mu with this small sphere? If the mass mu is not on the surface but at some depth, and the distance to the center is smaller than the radius of this small sphere. We have just considered this problem. The force of interaction will be like this one. The force of interaction between mass mu and mass m1, spherical mass m1, will be given by this formula. The force will be directly proportional to distance r1 from point mu to the center O of the small sphere. We have just obtained this result. And note that this coefficient is constant. Radius is not included in this coefficient. And we can always choose such a scale of measurement of the quantities like mass and density. We can always choose such a scale of representing the force on this graph. I'm choosing the scale for representing the force. I want to choose such a scale that this coefficient equals unity. It's easier. It will be very easy to carry out all the considerations. So if this coefficient is unity, we can always choose such a scale for representing forces. Then the force is equal in these units of measurement. Then the force is equal to radius. And so the force acting on this point will be equal to this radius. That will be the force of attraction of this body to the center of this sphere, if the sphere is filled with matter and has the total mass m1. I started from this simple case when everything is filled with matter. Then there will be a force acting here, F1, a force of interaction between this point mass and the spherical mass m1. Also, there will be another force of interaction between the mass m and the total sphere. I can imagine now I can switch on the total sphere if it's uniformly filled with mass. Then the force of interaction of this point mass with the big sphere will be equal to this radius. That will be force F2, the vector quantity, and this is also the vector quantity. Now we consider the total mass of a large sphere to consist of two parts. The first part is m1, which is here, and the second part is everything remaining, all the remaining part of mass m2. So the total mass m is certainly consists of two masses, m1 and m2. So the force of interaction with mass m1 is this force, and the force of interaction with total mass is this one. But the force of interaction with this is not F2, I'm sorry. This is the total mass F0. Total mass of interaction with a whole sphere when it's all uniformly filled with matter must equal to the vector sum of interaction with this small mass F1 and the larger mass m2. So in this equation we have a force F0 of interaction of point mass mu with the large sphere if it's filled with matter uniformly, and the force of interaction of the small mass mu with this mass m1 if it's here, if it's present, if there are no cavity, and then the force of interaction with the remaining mass m2, which certainly includes this cavity. What we don't know is F2, but this quantity, vector quantity, is known, and this is also known. So from here we can find F2, the force of interaction of our mass mu with the mass m2. With the mass m2. That will be F0 minus F1. F0 is known vector, F1 is known vector, and the difference between them is given by this vector, which will be the force of interaction between the point mass mu and the remaining mass m2. So now we have switched on this cavity. Now we remember, now we recall that the cavity is there. At first I started considering this problem assuming that there is no cavity, assuming that the mass is distributed evenly. And I assumed just that there is some volume filled with mass m1 and the remaining volume filled with mass m2. And I considered separately the interaction of this mass with the first volume m1 and with the remaining matter m2. So these two forces of interaction are simply calculated. We have solved this problem. And now I understand that the resulting interaction of mass mu with the sphere, with a large sphere which is has evenly distributed matter. Well, this vector of interaction consists of two forces: the force of interaction with a small sphere and the force of interaction with the remaining matter of mass m2. So it's easy to find the force F2. We have found it. That's the result. The force F2 equals the vector which connects the starting point, the center of small sphere, and the center of the large sphere. That is the force of interaction between the point mass mu and this region M2, which is here, when there is no mass inside the small sphere. So the reason behind this is very simple. If you have one body m1 and if you have another body m2, then any small body mu will be attracted to body f1 with the force f1 and will be attracted to body m2 with the force f2. And the total resulting force will be a vector sum of these two forces, and the vector sum is given by vector addition, like a diagonal of a parallelogram here. That will be the net force of interaction between this small body and the two given masses. So this principle of vector superposition of fields is used in this problem. Nothing more, just a vector superposition of fields. We have to calculate the interaction of this body with the small sphere if it's filled with matter, and with the remaining part, and we know that these two interactions will give you the interaction of the small body with the large sphere if it's filled totally uniformly with matter. So we have found the force of interaction between this body and the remaining mass when the large sphere has this cavity on this has this cavity. So we calculate the force of interaction with the remaining mass. The remaining mass is here. Note that this force is a vector connecting two centers, the center of small sphere and the center of large sphere. What will happen if we choose another point somewhere, a different point, here or here or here? The result will be the same. The force acting will be the same, because nothing will change. All the consideration will be the same. So inside this small cavity, spherical cavity, we have a uniform gravitational field directed along the line connecting the centers O and C. The uniform gravitational field, let me put it in this way again. I will draw the picture again, and the small sphere here. And so the uniform gravitational field will be like this. Whatever point you choose, you will have the same field, having the same direction and the same magnitude. The same magnitude and the same direction. So the gravitational field inside the spherical cavity, which is created inside the larger sphere uniformly filled with matter, the gravitational field inside this small spherical cavity will be a uniform field with all the forces absolutely identical, absolutely equal to one another in magnitude and in direction. That's it. That's the way of creating a uniform gravitational field. By the way, the gravitational field of the planet is not uniform. So this is a planet, and the gravitational field is not uniform. In different points, the direction of this force is different. The vector F1 is not equal to vector F2. They differ in direction, and they may differ in magnitude, because the farther you go, the longer distance, the smaller the force, and the closer to the planet, the larger the force. So all the forces differ in the gravitational field of the planet. All the forces are different. They differ in direction and in magnitude. This is non-uniform gravitational field. And here is uniform gravitational field. Inside this spherical cavity, the gravitational field is uniform. That's it. The end of this problem. Any questions? Okay. Today, as I promised you, we will go to a physical laboratory where we have demonstrational experiments which are demonstrated during the lectures in physics, if the lectures are given in the large physical class in the main building. That is on the 4th floor of the main building. Now we will all together, as a single group, go to the 4th floor of the main building, and I will show you some demonstrations, some physical experiments, and these experiments will be recorded on video, and this video file with demonstrations will be sent to all the students who have chosen to study distantly. All those who are on distant study will receive later today this video report about the physical experiment which I will show you, about the physical demonstration. So let it be the end of our lecture, and we will all together go to the main building, the fourth